So I'm going to talk about a categorical spectrum of TQFTs. We've heard sort of various things about it already yesterday. And I just want to talk about a project that I've been working on with Theo Johnson-Freyd for a long time now. And it sort of tells the story of what the collection of TQFTs, which sort of properties it might satisfy, and what that tells us about TQFTs. So mostly everything I'm going to say here is based on discussions with Theo. So let's sort of start with a little bit of sort of the motivation. Let me sort of start by saying, definitely for this talk, but I think also in real life, I don't really know what a quantum field theory is. And let me also say, I don't really know what a topological quantum field theory is in all details. Specifically in this talk, I don't want to presuppose any definition of a topological quantum field theory. I do not want to assume that a TQFT is a functor on some Bordesson category. However, whatever a TQFT is, you should be able to contemplate questions like the following. So suppose I have an n-dimensional TQFT A. And I have another n-dimensional TQFT B. You are allowed to ask, what are the sort of compatible, correct things I can do on boundaries, topological boundaries? So I can ask for the allowed n-1 dimensional, and now this could have sort of various names. You could call it boundary conditions. And this is again topological. Or it might be called defects. It might be called domain walls. And I might use any of these terms and I might mix these terms. It could be called extended operators. Okay. And I think I should be able to do with these is that if two of them, I can stack them. And I might also look at higher codimensional domain walls between them and stack these. And the algebraic structure that describes such stacking is the data of an n category. So let me make the following assumption. For this assumption 0, n-dimensional TQFTs and their domain walls and their defects form an n category. And let me call this n category TQFT superscript n. And this is not just an n category. This n category has a preferred element with a preferred object, which we can write 1 to the n in TQFT n. And this preferred object is called the trivial theory or the vacuum. This is called vacuum. Great. And moreover, here's the thing you can do with these. If I have, moreover, if I take loops of TQFT, which by definition for me means the endomorphisms in TQFT n of 1, this is the same. What is this? So this is a defect, a domain wall between two trivial theories. And the domain wall between trivial theories is just a theory 1 dimension below. So this should just be TQFT n. Okay. So these are things, I think, if you believe in there being some abstract concept of what a TQFT is, it should sort of assemble into such data.
Excuse me. Here, domain wall may means gap domain wall. Do not include the gapless domain wall. I understand.
Yes, definitely. So I mean, really topological. So it should be something that behaves topologically. And I guess a gap thing would be an example of such a thing a priori. That's right. So it needs to be a topological domain wall. And I really just consider TQFTs, their topological domain walls and topological domain walls between these and so on and so forth. And this forms an n category. And I can say this about this n category. And I think this idea, I'd say, goes back at least to Kapustin. I don't know whether this is even older, this idea that TQFTs in their domain walls should assemble into a higher category. Now, I should say, implementing this for a concrete model, for the TQFTs might be very hard. But in this talk, the game plan will be to just sort of go with this. So game plan, impose reasonable, of course, that's what's really fun to debate, assumptions on TQFTN, or maybe on a nice and well-behaved subcategory, depending on how you like the assumptions. That pin it down. Uniquely. And this will sort of be a bit in the spirit of Konstantin's talk yesterday, where he mentioned that for him, these higher categories, it's mostly that the sort of computations you actually do will be homotopical computations. And they're sort of just an organizational tool. And this is sort of similar in a way that I'm imposing a strong condition in how this looks up to homotopy, the invertible part, and then fairly mild conditions on the general structure, and that already pins it down completely. As a quick comment, maybe sort of so far I haven't done anything. This is the only sort of mathematical assumption I've made so far. I now make a few more assumptions. Before I make these assumptions, I want to say something which is not mathematics, but just to give you an idea of what sort of TQFTs I'm looking at. Sort of if you want to sort of in your head follow along with the assumptions, I now tell you sort of the flavor of TQFT that I want to talk about. And this will be sort of a physical comment, right? I'm not saying anything mathematical yet. The flavor of TQFTs that you should sort of have in your mind when you follow this talk are absolute TFTs, meaning they've trivialized anomaly. They should be sort of defined, or their partition function should make sense on framed manifolds. In other words, I have no space-time symmetry, no global symmetry around. These TFTs that I consider here will be non-unitary, or not necessarily unitary. They will really be discrete. So I'm not going to talk about deformation classes of TQFTs. I'll talk about TQFTs up to isomorphism. And they will be very finite. Sometimes it's called compact. What I mean by that is they should have partition functions that are defined on all manifolds with the correct symmetry type. And you shouldn't exclude certain manifolds. So there are no infinities in these TQFTs that I consider. They'll be really very finite beasts. I should say this condition is easy to lift, because if you want to have an anomalous theory, you just look at a twisted or relative theory, as we've seen in Jackson's talk. So this is, once you understand this, you understand the anomalous theories as well. This one is easy to lift because there's some descent problem here. You can sort of impose any structure group if you understand the frame setting. These three things I think of as being intimately connected, and they are much harder to lift. I think you really want to go to some world where you have a unitary TFTs, and it's really governed by infinite dimensional Hilbert spaces and phenomenon algebras and so on. So that part is sort of very interesting.
There's a question in the chat.
Yes.
Says you're thinking as a TQFT as the category of functor of coordinating manifolds correct? And if so, it is not clear how the superior categories, natural transformations, and so on, this loop space is the n-1 category.
Yeah, so I am specifically not thinking of a TQFT as a functor on a Boltzmann category. I really want to take the perspective of a TQFT is just whatever. I'm just going to write down axioms now, and you just tell me whether these axioms match with the thing that you have in your mind. And in particular, if you do consider, so you wouldn't, if you want to think of it in terms of Boltzmann categories, then the sort of delooping story, what you look at is lax transformations between these TFTs. So you really want to look at defects between your TFTs, isomorphisms, not natural transformations between Boltzmann functors will always be invertibles, but those will just be isomorphism of TFTs. No, and I'm considering defects of TFTs here. So that's important. But so you could sort of, that would still fit in a Boltzmann functor world. Okay. So now let me do a little bit of mathematics. This is something that Konstantin called anti-category yesterday. I call it a categorical spectrum. A categorical spectrum is a collection of pointed n categories so pointed just meaning with a preferred object and equivalences omega Cn is equivalent to Cn minus 1.
So are your C symmetric monoid?
I don't have to ask this, but it will automatically be from this definition. Just like in a spectrum, the n space is always an infinite loop space. Do we have something to grab at the top board?
You have to pull on the edges.
I remember.
Yeah.
That's right. This one.
So upward you push, and if you want to get them down, you push.
But I can't push it further. That was the question.
You pull it down and get
I see.
yes.
Oops. No.
Does it say word for seamless A? Okay, but it's more important that they see the bottom yes that I'm writing on. Okay. So assumption 0. So first of all, maybe I should say some names. This notion of categorical spectrum and how it's related to actual spectra is currently studied a lot. Some people to name here. There's Naruki Masuda, who is in Hamburg with us, and then here in Bonn, Mr. Gärtner. And so this is like really rapidly developing the subject of categorical spectrum. And as Peter was just asking, this makes.
You can't see that. It's in the shadows. You got to move the boards up.
Better this way?
Yes.
Yes.
Fantastic. Okay. So this makes Cn or C upper n into a symmetric monoidal category. So this meaning you have these infinity loopings. Cn appears as the endomorphism of a unit object in some Cn plus 1. And so this makes it symmetric monoidal. And in particular, it allows me to look at Cn cross, which is the subcategory of invertible objects. And invertible morphisms and so on. And this is an infinity group board. Or a fixed homotopy. And so therefore what you see is that if I have a categorical spectrum, I can just look at the Cn crosses, those form spaces or homotopy types with these various loopings. And so what they form is an actual spectrum in the sense of homotopy theory. So what you get here is a function from categorical spectra to actual homotopical spectra or generalized homology theories as we've seen them, which sends one of these Cn's to these Cn crosses with their loop equivalences. And in particular, it will send this categorical spectrum, which is called TQFTN, to a categorical spectrum I call TQFT, to an actual spectrum I call TQFTN cross. And this is the spectrum of invertible TQFTs. This is the invertible TQFTs. So this is all stuff you just get out of assumption 0. So let me say a little bit about indexing. This also already came up in Konstantin's talk. I think of the reason I use upper letters here to index these is that this is essentially a cohomological convention. I have a category C0. Let's think of it this way. And then I have my category C1, which places objects below C0. So C1, the loops of C1 is C0. And I have a category C2, which has new objects, but the 1 and 2 morphisms are governed by C1. And so I think of the objects of C0 as being the 0 cells in my spectrum, in my categorical spectrum. The objects of C1 are the -1 cells in my categorical spectrum. The objects of C2 are my -2 cells. Right? So these are the 0-dimensional TFTs. These are the 1-dimensional TQFTs. And these are the two-dimensional TQFTs and so on. So you should think of a categorical spectrum as defined here, at least, as a maybe co-connective categorical spectrum. It just has sort of cells negative degrees. Doesn't have cells in positive degrees. I could more general, there's a more general definition of categorical spectrum where instead of n categories, it's infinity categories. And then I would have cells in all degrees. And the way you should think of this structure is that a spectrum is a thing which has cells at all levels in negative and in positive degrees. So if a category is a thing which just has things in positive degrees, a space is a thing which just has invertible cells in positive degrees. A spectrum is a thing which has cells in all degrees and they're all invertible. And a categorical spectrum is the thing which has cells in all degrees and they're all non-invertible. So that's the idea. So this is sort of the most general piece. This is categorical spectrum. Okay.
Now we can also like for spectra, right? I mean, they're not just committed monoline spaces, but they're also group-like.
Yeah.
Can you repeat?
What is the appropriate notion of group-like? Here, like are all objects invertible?
Can
you repeat the question?
So the question was for a spectrum, or I would paraphrase the question, you tell me whether it still matches your question. For a spectrum, you're saying this is not just an infinity group-like. You learn that this is a group-like infinity spectrum. It's a monoid group-like infinity spectrum, and indeed every object here is invertible. So this will have, this is a groupoid that suffices. It's a pointed groupoid that suffices to show it's a spectrum. But by delooping it, it inherits a commutative monoid structure, and in fact, everything is invertible by definition here.
No, but the question was whether all objects in Cn were invertible.
No, but Cn is just a categorical spectrum. So there you just have a commutative monoid.
So
if the zero, all of these in a categorical spectrum, all of the Cn's will inherit symmetric monoidal structures, but no invertibility. The categorical spectra don't have any invertibility a priori. Okay, so now so far I've basically done nothing. I've just reformulated assumption 0. Let me make assumption 1. So a priori, I said a spectrum, everything is invertible. In a categorical spectrum, nothing is invertible. So that makes categorical spectra really hard to work with. But these spectra of TQFTs, they are sort of a nice middle ground, because what happens there is not that the cells are invertible, but the cells are adjunctable. And so this gets for various things, makes your world move closer to homotopy theory. And in particular, what I ask is that this categorical spectrum, TQFT bullet maybe, has adjoints or duals.
There's a question in the chat also. When you say invertible TQFT, is that a natural transformation in which each component is invertible, or are we still thinking in general? And how is this that a spectrum? Is this a spectrum in some sense?
Yeah, it's very important that I still don't think of it as a natural transformation. I think of it as an invertible defect. So this comes to question of, if you're sort of into categories, comes to question of univalence or rest completeness, that I really ask for invertible defects, and they might be different to isomorphisms of TQFTs. But I really mean invertibility defined in terms of the structure that I already have. So if I have an n category, I assume it's a univalent n category. I know what invertibility means. Okay. So it has adjoints for k morphisms for all negative k. In other words, for any strictly positive dimensional TFT, possibly between other TQFTs, I get, so let's call this X. I get a thing called X bar, maybe, and things look like this. Just writing down the junction equations such that there are isomorphisms like this, like this. And on the other side as well as on the right. Or on the left, I guess, as well as on the other side. Okay. So I think probably everyone here is, well, most of you might be familiar with that condition. And this really just means, in words, you're allowed to wiggle your TFTs around. These are really supposed to be topological domain words, so surely you should be able to sort of bend them around. This is the sort of condition that already breaks if you consider sort of slightly less finite and less discrete TFTs. But for these purposes here, I'll sort of stick with that. Yes.
Yeah, manifolds are real, right?
They are, so for me, these, so if you want to, so I've not said anything about manifolds, so I'm not really parsing your question, but the question was, are the manifolds that I'm considering here oriented? And if you want to think in terms of manifolds, you should think in terms of frame manifolds. So I just really just ask every K-morphism has a right and a left adjoint. So these are not oriented, but frame oriented. Okay. So again, so far I haven't made that many assumptions. Now I want to sort of get actually into TQFTs and sort of pin.
Put this for the lowers on the other side. You can see it.
That's right. That's a good idea. It's a good idea. That's still visible. So
Yep, thank you.
the relevant part is visible. Okay, so let's actually get into this particular categorical spectrum, and let's sort of stop talking about abstract nonsense, and let's do 1D TQFTs. So TQFT1 is the one category of 0 plus 1 of sort of one-dimensional, so 0 plus 1-dimensional if you're a convinced metaphysicist, TQFTs. And so let me just tell you what I assume these are. This is now assumption 2. Well, what is this? It's a TQFT morally where you have state spaces assigned to 0 manifolds and where you have, you know, maps, partition functions assigned to 1 manifolds. And the data of such a thing, you know, if you have the state space of your 0 manifold, this is some finite dimensional Hilbert space or finite dimensional vector space. It's a TQFT. You don't have any Hamiltonian or anything like this. So it would just be a vector space. But I really want to consider sort of all TQFTs in all generality. So it should be a super vector space. So I do want to know. So this is a finite dimensional super vector space over the complex numbers that I assume as a, like, use sort of as a discrete ring here. So sort of the first severe restriction I've made is to say I think of the complex numbers as a discrete ring. Okay. So far the conditions are still harmless. Now, up to the next condition, additivity. So this is now sort of a bit of global structure or global properties that this categorical spectrum satisfies. So this is assumption 3. Assumption 3 comes in two parts. The first part is that this spectrum TQFTN has direct sums and 0 at all levels. So formally, for those of you who know the terminology, this is a sort of TQFT super N is a 0 semi-additive or semi-additive in infinity impact. Okay, but this just means you can take the direct sum of TQFTs. What this morally supposed to be is you take the direct sum of state spaces, and you're sort of for the direct sum of TFTs, it will have sort of the direct sum of state spaces, and it will just have the sum of partition functions. And the 0 TFT is the one which assigns the 0 vector space as a state space to everything, and it assigns the 0 map as partition function. So that's believable. And the other assumption is somewhat more interesting. TQFT is the higher categorical version of idempotent complete. I give sort of a few perspectives on this. Is higher idempotent complete. So this is also known as sort of by now at least 3 names in the literature. They all sort of highlight different aspects of this concept. You could say this is condensation complete. And it's also known in rich category literature Cauchy complete. And it's really categorically, it's a close analog of being Cauchy complete in the sense of a metric space. And this is higher these conditions at all levels. So this condition, I think, the higher idempotent completeness goes back to a paper by Theo Johnson-Freyd. Implementing this sort of rigorously with infinity n categories is currently being done by my student Marcus Seto. And this is closely analogous to something that Niels will talk about, I think, tomorrow. It is these orbifold completions. I also mentioned these.
The making idea that can have anything to do with idempotence that we think about
yes, so this is just a higher categorical version of being idempotent complete in the sense of an infinity one category. So if you haven't, was that the question?
Well, no, I mean that I assume, but I don't see like what's different. Like
okay, so I do not want to write down the definition, but you can come after the talk to me and I'll tell you the definition. I will give some sort of intuition for what this means, but I think otherwise the talk will just sort of go far afield. So the
just a quick thing. It's hard to see the very last name you wrote over here.
Yeah. It's Gregor Schaumann.
Thank you.
Okay. Okay, now I can remove this top board. So let me just say 5 sentences, maybe a bit more about this condition, but I really don't want to stick with it for too long. You should think of this as sort of the most harmless completion you could sort of perform in infinity n categories. A way to say what this means, now I'll just give you sort of 3 different perspectives and you just pick the perspective you like best. A way to say what this means is that TQFTn has all absolute colimits. This is sort of the category theorist perspective in this, where absolute colimits are by definition the columns preserved by all additive functors. So this really means those are morally those you should think of this as the equational colimits. The colimits you can check by checking some equations, and equations are preserved by all functors. That's sort of the moral reason why this is true. Let me say, but how you could think of this physically. If you're sort of a physicist, the way you want to think of this is to say, physically what this means. And there's sort of an argument in this paper by Theo and Davide Gaiotto, how to think of this physically. The way you should think of this, and I won't explain why, I'll just tell you, is that if you have commuting projector Hamiltonian lattice models, in a TQFTA, these produce a new TQFTB. You're sort of allowed to take these and consider them as a new TQFTB.
So there's again a question in the chat. It's asking if the sum in the TQFT in the classical examples is relates the 2 systems interacting for a new manifold, which makes cobording. And if the original boundaries in some sense are not more important. So I hope I understood it correctly.
So I think so my answer is, I would say no. the sum just means you really just take the sum of the underlying vector spaces. If you have state spaces, if a TFT assigns state spaces to anything, just take the sum of the state spaces. That's what the sum of the TFT is doing. So I think there's no geometric, like the sum is just something algebraic. Okay, the other, so this just means if I have a TQFT A and I have a commuting projector Hamiltonian lattice model inside of my TQFT A, I can produce a new TQFT B. Another way to say this is if you have a state sum construction you can build inside of the TQFT A, that gives you a new TQFT B. And in particular, and this is harks back to Konstantin's talk, if you are in characteristic 0, which I am here because I talk about the complex numbers, this imply, and that's sort of the all-important property that gets implied by this, is that you can, if I have a TQFT A and I have a finite discrete symmetry, maybe a higher form finite discrete symmetry, I can gauge it and get a new TQFT. So this sort of includes gauging finite symmetries. And mathematically, what this means is that this is infinity semi-additive at all levels. So you have sort of ambidexterity in the sense of Hopkins theory. Okay. Let's see which condition I'm removing. I think I removed this one.
And here, the theory you get is sub theory of the thing you had before.
The theory you get is a new theory, which has an interesting domain wall to your old theory. I wouldn't call it sub or anything. There's no sort of sense in which it's sub. But it's just a different theory, which is connected to your old theory. And the point being, just from a physical perspective, well, I've told you a way to produce a new TQFT from an old one. So surely that new TFT should also be in the categorical spectrum called TQFTs. This is like the easiest way to produce new TQFTs. And this way should, like, you should allow these, is what I'm saying. So you might be able to produce many more complicated TFTs, but at least you will be able to produce these, and so you should allow them. That's the argument. Let me sort of say one more thing on this and then move on. Algebraically, what you have is you can sort of consider these additive categorical spectra with adjoints. And then I have this Cauchy complete, sort of this additional higher idempotent condition. These guys. That's a full sub category. This will always have a left adjoint, which is a completion operation. And so you could think you can always go and take your additive categorical spectra and complete it for free. So even if your thing you're giving me doesn't have all of these state sum constructions in it, I can just sort of add them in without a problem. But this is algebraically interesting. This already brings in sort of a lot of interesting objects into TFTs that sort of already includes all the state sum constructions. Namely, I have a functor from commutative rings sits fully faithfully in this categorical spectra. This takes a ring R and just sends it to a categorical spectrum you could call B bullet R, which essentially has nothing everywhere. That's a point, identities everywhere. And it has a ring sitting in degree 0. And then again, it has just nothing below it. So this is in degree 0. And now you can send this over along this completion operation. And say, now I want to add in all of these nice absolute colimits. And then I get a thing you could call B head of R. And this is algebraically nice. If you unpack this, B head 1 of R is the finitely generated projectors R modules. B head 2 of R is the separable R algebras. And Morita equivalences, or and bimodules with category. And at least when I'm working with a field, if I do d hat 3 of k, this will be something like the 3 category of multi-fusion categories over k, and the bimodule categories. And b hat 4 of k, this will be in characteristic 0 for an algebra. So let's do b hat 4 of c for an algebraic closed field characteristic 0. The following is true. This will be what Jackson called Burfuse, or sort of a multi-version of Burfuse. So more generally, we have something called multi-fusion 2 categories. But in characteristic 0 algebraically closed, this will always be equivalent to predicate fusion categories. Okay. So you see in higher dimensions, you get sort of interesting algebraic structures coming out of that, but these algebraic structures are very, very finite. And that's sort of what this completion operation is doing. This really just throws in sort of the most finite things you can do.
What kind of categories do you treat the domain and codomain of the C-junction?
Infinity 1 categories, or I mean, in this case, yeah, no, infinity 1 categories. Okay. All right. So far, this is just structural assumptions and a little bit of an assumption on what TQFT1 is. So at some point, I have to impose some more severe restriction. Right? I want to pin this down uniquely, this categorical spectrum, so I have to say something at some point. And this will happen now. So let me sort of look at invertible TQFTs. So this is the question, who is the spectrum TQFT cross? Who is sort of the underlying actual spectrum? And let me just record some things I've already told you. We already know that TQFT1 is supervector spaces over the discrete complex numbers. So we find that TQFT0 is just the complex numbers. And so in particular, and this will in particular imply that all of the higher TQFTn categories are in fact complex linear, because this will act on everything. So this means in particular that TQFT0 cross, the invertibles in TQFT0 is just the invertibles element in this commutative ring. This is C cross. And now here's the thing that Mike Hopkins already explained with this lecture. Whenever I have a spectrum where the top bit looks like C cross, you get a canonical comparison map to something you can think of the universal spectrum where the top bit looks like C cross. And this is this brown compass spectrum. So let me remind how this goes. There is a unique spectrum, unique up to non-unique isomorphism. IC cross such that for all x in spectra, the map from pi0 from how did I call x? X is my spectrum x to IC cross. The map which just looks at this map at the level of pi0, just goes from POM. This one happens in spectra. This one here happens in unique groups from pi0x to C cross is an ISO. This is an ISO. Okay. This is pretty cool. This sort of characterizes the spectrum just by looking at what maps into it do at the level of pi0, which is very powerful. And in particular, what this means, since I already know that TQFT0 crosses the C cross, I can find that pi0 of my TQFT category of my TQFT spectrum is C cross. And hence I do get, well, I can use the identity map here, and I can lift this therefore to a homotopically unique map from TQFT cross to IC cross. So I get a map.
Would you pull the board down?
This way?
Yeah.
That's good. Thank you.
I get a map from TQFT cross to IC cross just by this equation here. Right? Just take the identity here and lift it up. And in fact, it's not just a map, it's a map which is an isomorphism at the level of pi0. That's the identity at the level of pi0. And the next assumption, this is maybe the most severe assumption I'm going to impose, I later sort of motivated a little bit, is an assumption due to Freed and Hopkins, who argue very nicely in their reflection positivity paper that whoever the spectrum of discrete invertible TQFTs should be, discrete invertible frame TQFTs, it should look like IC cross. So the assumption is that this map TQFT cross to IC cross is implicit. So now I've really imposed some strong constraints on this category, but I sort of I keep going. And let me sort of say a little bit about the motivation. This is essentially taken from Freed and Hopkins.
Sorry,
Yeah.
I missed why there's the identity on the right hand side.
Oh, because pi 0 of TQFT is C cross. And so if you take as X the spectrum called TQFT, or invertible TQFT, you will find pi 0 X is C cross. You have Hom from C cross to C cross. There's an element in the Hom from C cross to C cross called the identity on C cross.
But is it also C cross if the super index is not 0?
No, but I only need pi 0 here. I just need to know pi 0 of X, and X is the spectrum. So I just need the cells at level 0. And that's just the C cross.
Thank you.
Okay, so the motivation, for those of you who are not familiar with this, is that if you look at pi minus k of IC cross, this is something that Mike spelled out in his lecture theories. This is Hom. By definition, this is Hom in spectra from the minus k's here into IC cross and pi 0 of this, which is by this statement here, Hom in abelian groups from pi 0 of the sphere shifted, and I've sort of arranged the shift so that this is just pi k of the sphere into C cross, and by Pontryagin-Thom, pi k of the sphere spectrum is the Bodison group of stably framed K-manifolds. Stably framed into C cross. And if you unravel, okay, and so then this map, so we have the map TQFT from, if you want, k-dimensional invertible TFTs, which is pi minus k of TQFT cross to this that we've just built. What is this doing if you unravel the Pontryagin-Thom isomorphism? It essentially takes a k-dimensional invertible TQFT and evaluates its partition function on stably framed manifolds. So the way you can think of this conjecture, of this assumption, is that a k-dimensional invertible TQFT is completely determined by its partition function on stably framed manifold. So this is the map. This is called, if you want, okay, so let me reiterate in this talk. I'm writing down assumptions. These are mathematically correct statements. These are mathematical statements that parse. And then in between these assumptions, I'm just giving you sort of motivation and ideas. And so you can sort of have, take offense with everything I'm saying between these assumptions. But assumptions, I think, I have things I'm allowed to just say. And later I write down a theorem using these assumptions. But so assumption 4, the way you should read it, is that invertible k-dimensional theories are completely determined by the partition functions on stably framed manifolds. Okay. And this, of course, this sort of is where the symmetry type of my ambient spacetime comes in, when sort of really saying everything is just stably framed. I'm not imposing that this is a bosonic theory or the sort of the minimal symmetry that you could have. So TFT, and again, sort of by descent, as in Mike Hopkins' talk, you can get other categorical spectra of TFTs with other symmetries out. Okay, so this is 4 assumptions now. We've assumed we have adjoints. We've assumed it forms a categorical spectrum. We've assumed that we know how the top level looks like supervector spaces. We've assumed that we have direct sums in these high idempotents, and we've assumed that it looks like IC cross. Now there's a single more assumption that I have to make, and then it's uniquely determined. And the additional assumption I write on this board, I try to make sure that all assumptions are still up. by the time of writing the theorem. So this assumption is slightly annoying, and there are sort of various ways you can try to get around it, but I'll write the assumption as it is. So this is the assumption of semi-simplicity that we have to currently impose by hand. Semi-simplicity. So this is assumption 5. And this assumption says for all one-dimensional TFTs, so -1 cells, for all one-dimensional TFTs, possibly between other TFTs, so for all one-dimensional domain warps, i.e. -1 cells in the spectrum. The algebra, let's call this F. The algebra NF, this is now actually just an algebra in just a linear algebra over the complex numbers by all the assumptions that we've made so far, is a finite dimensional and semi-simple. So it's a finite sum of matrix algebras. Right? So what does this algebra look like in terms of TFTs? It's if I have some TFTs and some defects and whatnot, and then here might have a defect, here might have a defect, there have a line defect. Then what these algebras are the algebras of point operators, the algebras of things that live on such a line. And they can fuse together, that forms an algebra. And the condition is that this algebra is semi-simple. So let me justify this condition a little bit, or say why at least this is a reasonable subcollection of TQFTs you could consider. For example, and this is sort of where we are currently moving into, is that if you would consider unitary TQFTs, where everything is sort of, if everything has a compatible star structure, or dagger structure, so that all algebras, all these algebras are C-star algebra. Then this condition is automatic, because together with the rigidity with all of these adjunctions, it would imply that all these algebras are finite dimensional C-star algebras, and those are automatically semi-simple. And automatic. So in sort of a version of the story, which we don't yet have, but in a version of the story where it starts with unitary TFTs, you wouldn't have to impose this condition, which is quite, I mean, we don't yet have this version of the story, so I can't really say this, but because of that, I'm very sure that it's just, you can sort of automatically move into this world. Okay, fine. So now, where is, I think I'll use this board. My board organization is horrible. I want to make sure that the t-state just makes assumptions stay. So then we can. So now we can finally profit. So here's a theorem. So yesterday evening in Theo's talk, I've learned that this is due in 2026. So that was interesting news for me. Good. There is this a unique categorical spectrum. Let's call it, or we tend to call it W. I think because W is the letter after V, and V looks like vector spaces, but I might still change. satisfying this condition. Okay, so these conditions, let me sort of remind what these conditions are. We have a categorical spectrum. Its top part looks, it has adjoints. Its top part looks like simple vector spaces. Its invertibles look like IC cross. And all of these little algebras that sit sort of at the very top are semi-simple. These conditions, if you sort of believe, at least in the subworld of TFTs which look like this pins down the subworld completely.
What's an equivalence of categorical spectrum?
You could
Uniqueness is absolutely come to some stabilization.
when it's defined in terms of sort of loop spectra, so it's really just the limit, sort of it's a limit of categories as a categorical spectrum. So it's just a sort of level-wise. Because it's a loop spectrum, I don't have to cofinitely replace anything.
And categories are equivalent.
Yeah, exactly. The n categories are equivalent compatible with the looping.
You do the same W as yesterday.
Yeah, I get to this. This will be the next sentence. It's almost, it's not quite. Yeah.
How robust is this? If you change the vector space to something else, is it still true that it's unique?
Yeah, that's a good question. And I will get back to this after the next paragraph, answering Alexei's question. So, right. So your question was, is this related to the separable or Galois closure of the complex numbers that Theo was talking about? And I'm saying it's closely related. I wouldn't say exactly how it's related, but it basically sort of, there's a few cells in degree 4. Like in degree 4, it starts to look different, and in degree 0, but otherwise it's sort of the same. It is closely related and this is how we originally started to think of this, but from this you can extract this theorem or version of this theorem. It's closely related to what Theo yesterday talked about, the Galois closure, and it's sort of the versal if you want. It's not universal because it's not unique up to unique isomorphism, but it's unique up to non-unique isomorphism, Galois closure. Well, Galois closure means sort of the universal Galois extension. W's made is separable of, I'm just saying, this categorical spectrum. So you can sort of work out what it means to be a Galois extension in categorical spectra. And then you find that there are interesting Galois extensions of this guy. And then you can ask yourself what sort of the universal Galois extension, which doesn't have any interesting Galois extensions anymore. And this turns out to be a thing called W separable. And they are closely related because if you sort of the way you build this W is essentially related to how you build a, this you could also call a separable closure. And it's closely related to how you build a separable closure. And what you here do is sort of, we're basically developing a variant of Kummer theory. So we go and look at the roots of unities of the thing you've built, and ultimately the roots of unity. So here all the invertibles look like IC cross. And in this world, only the roots of unity, so the torsion amongst invertibles, looks like an I-human cell. And then you sort of try to get closer and closer to this guy. But the way to build this actually works here as well. So you can also build something which looks like IC cross. And this gets me back to your question. I mean, this is just, you know, I don't want to say much more about it just because Theo talked about this yesterday and I wanted to make this connection. Building this, you could think of as sort of killing some entire space or some entire homotopy type of that category. And imposing what the invertibles are, it's like fixing the homology. And imposing what sort of the 0-1 level is like fixing the fundamental groupoid. And SVEC is already separable closed or Galois closed. So this will have trivial fundamental groupoid. So roughly what the assumptions are doing here is that it says my fundamental groupoid is trivial. And it says my homology is sort of appropriately trivial. So it is a sort of Horowitz type theorem that's running here. So if you would use another TQFT1, this will be, you know, if I'm still semi-simple, this will look like representations maybe of some supergroup. This theorem wouldn't necessarily be applied because then I have interesting fundamental groupoid and then I can't just check. Then I don't just get sort of a Horowitz type theorem, but I sort of just need to check the homology. Then I think I'd have to look at more than just invertible part in higher dimensions. That's just an intuition, but that's sort of, I strictly think you have to assume that intractability there. Okay. So this is the theorem. I just want to say, I just want to give sort of a little bit of a feeling how this looks like in low dimensions, and then I'll stop. Well, let me do this just here. So, yeah, let me just give sort of an impressionistic view again, as this whole talk sort of is. So let me write down the homotopy groups of IC cross, and below that, let me write down what the objects in this W are. So first, I have my C cross, and then in W0, there's just a C. Okay, great. Right, W is the thing I previously called TQFT. And then pi minus 1 is a C mod 2. This is if you want to invertible 1D TQFTs, and W1 is my supervector spaces, finite dimensional. And of course, I have two interesting simple objects. So simples, I should say, in any one of these categories satisfying these conditions, you can say an object is simple if it's indecomposable under the direct sum, which is equivalent to saying that the top endomorphisms of that object, the sort of scalars that fly around in one of these objects, is just one-dimensional. So I always sort of study these categories by looking at the simple objects. So here I have the unit and the odd line. But even in the odd line, you could say this is the fermion and this is the boson. And interestingly, there is no non-zero morphism between them. Then one level higher, you have C mod 2 again. This is pi 2 of the sphere. This is invertible 2D TFTs. And in W2, you find that this is the category of finite dimensional superalgebra. So we'll see the Morita category of these. And in particular, you have two interesting simples, which are in fact invertible. That's the trivial algebra, and it's Cliff 1. That's the Clifford algebra. And but now what happens is that there does exist a non-zero morphism between them. So I want you to think that there's sort of more interesting information, and this can be sort of heavily exploited later. There's really interesting information in the non-invertible structure of this category. And now to W3, pi minus 3 is a C mod 24. And W3, very roughly, the simples up to ISO are essentially rated equivalence classes. Of super non-degenerate. This is sort of a framed version of a supermodular category, which is a fermionic version of a modular category of super non-degenerate. Braided fusion categories. With a lift of the central charge. With a lift of central charge. And I guess it just makes sense if the terminology makes sense to you, but from it's sort of defined usually in Q mod 1/2 set to Q mod squares. So sort of a 24 lift. And there exists a non-zero morphism between two of these, if and only if they define the same element in some C mod 24 lift of the Witt group, of the super Witt group. So there's sort of many simple objects up to isomorphism, and then you can ask when are they connected, and that imposes some pretty severe equivalence relation. And I should say, this W3 sort of we started, or this project started from sort of what was inspired by a construction of Freed which is motivated from this question: can you extend Reshetikin Derivative theories to the point? Because an object, if you want, is a Reshetikin, a sort of a super Reshetikin Derivative theory. And this leaves now as objects in a nice and linear 3 category. right? This is really a 3 category, which is additive and linear and everything, and it has these things sitting there. And you really see with this sort of, I said, 2 of them are connected if they're the same element in the Witt group. So I think they're really connected to the trivial theory, if and only if it is a center. But you have lots of things that are not centers, and they're just different objects in this category that are not connected to.
So I think it's C1 board there.
Sorry? Q mod, sorry, yeah, Q mod 1/2 said. I mean, this is in the end, it's just a normalization convention, but there's a thing called central charge, and you can define it as being a number valued in Q mod 1/2 set. And you lift it up to something Q mod 12 set. Well, the reason you start with calling this Q mod 1/2 set rather than Q mod set, this comes from physics, essentially. It's because if you build it in terms of conformal theories, there's actually an actual Q number. And there is sort of, that's how it's normalized. Okay. Right. Okay. To end, since I'm out of time, I just want to say a few words what you can do with this W, and then I'll stop. What you can now do is you can use this to study, say, questions like which invertible theories in n dimensions do admit a boundary, a sort of gap boundary theory or a topological boundary theory, or at least sort of amongst these things. And so what you then start to study is exactly what Jackson was talking about, an invertible object in W together with a non-invertible boundary to trivial. And in fact, maybe let's say this a little bit. Okay. You can look at these invertible NB theories plus non-invertible boundary plus, and let me sort of ask this to be a simple boundary, so indecomposable, up to sort of the iso of Wahl and the obvious equivalence relation and non-zero domain mode between the boundaries. If there's such a thing, you can forget the boundary and just think of this as an invertible theory. You just remember the twist. Up to iso. And if you have such a thing, you can forget that it's invertible and just consider it as a simple TFT. Simple indeed TFT. Up to any non-zero domain. Okay, so we've seen this here, that this is an interesting map. The invertibles were C2 and super algebras, but the simplest up to domain wall was just trivial because they were all connected to one another. And the point is, this forms a long exact sequence. You can sort of already see it here. If I have an invertible with a simple boundary, here, okay, if I have the image here are the invertibles that admit a simple boundary, and the kernel here are the invertibles which, well, admit a simple boundary. So this forms a long exact sequence, it goes around, and in dimensions greater or equal to 5, you can actually compute this term, the anomalous theories. And those are all, this is something that Konstantin mentioned briefly, those are essentially the Gauss sum theories. And so there's some L group that appears here that this sort of computes this in dimensions greater or equal to 5. And using that and this map, you can figure out things about this guy. And so, for example, a thing we find is that the only invertible theories in the image here are the Arf-Covariant variants. And so what you learn is that if you have an invertible theory, which is interesting and which admits a gap boundary, it has to be an Arf-Covariant variant. So this Cliff 1 gives you the 2-dimensional Arf-Covariant variant, and this continues to hold for all the Arf-Covariant variants, and no other invertible theory will admit a gap boundary of this sort of semi-simple flavor. That's right. And then sort of, and here sort of connects on the talk of Theo from yesterday evening, where this exact sequence you get looks sort of amazingly close to the PA surgery sequence, where the L theory that appears here is slightly different. It's sort of a finite version of the A theory that appears in PA surgery, but it sort of starts to move amazingly close to that story. And we really currently don't have a good way to say why, other than it's sort of, the proofs are sort of mirrored. It's sort of a linearist version of it. Yeah. So that's the end of my talk. Thank you.